Okay, ladies and gents, welcome to Year 10 homework number 2, the exam corrections. So this exam is on forces and elasticity. So let's dive right in. Make sure you've got a blue pen and green pen ready to make your annotations and your corrections. So question 1 says a Newton meter measures the weight of objects, and look at figure 1, and there we can see a Newton meter with a weight on the end. And the first question asks, what is the weight of the object in figure 1? So we just need to check the Newton meter, and we see that the reading is halfway between 5 and 6, so the weight is just going to be 5.5 newtons. Okay, so over the page. Alright, part B says the spring inside the Newton meter behaves elastically. So what happens to the length of the spring when the object is removed from the Newton meter? So the key word here is elastically. So if something behaves elastically, that means that when a force is removed, the object returns to its original length. So that's what elastically means. So what happens to the length of the spring when the object is removed from the Newton meter? So if we remove the object, then the spring is going to go back to its original length, which means the only sensible option here is it's going to get shorter. So that is the box that we tick. 1C, a student carried out a practical to investigate the extension of a spring. Write a method the student could have used. You do not need to mention safety precautions. So this sentence really important, which means we shouldn't be mentioning anything about safety goggles or weights or being careful, because it will not get us any marks. So there are 4 points you need to include here. I'm going to write them out in bullet point form. The very first one for the first mark is to talk about setting up a clamp stand and then hanging a spring from that clamp stand. Okay, now that's not going to get you the first mark, because we also need to talk about using a second clamp stand and fixing a ruler next to the spring. So that ruler is going to allow us to measure the extension of our spring, and we need it fixed in place next to it. So that bullet point, that whole one, is for the first mark. The second mark is then for talking about measuring the original length of the spring before you've put any weight on it. So we would just say measure the original length of the spring, and that is mark number 2. Then the third mark is to then talk about, well, how are we going to actually extend the spring? So we are going to hang a weight from the spring, but we need to go a little bit more than that to get the full mark. So the next thing, after you've hung the weight from the spring, you need to measure the new length and then calculate the extension. And you're still not going to get that full third mark unless you clearly explain how you're going to calculate extension. So I'm going to put this in brackets. We're going to do new length subtract original length. And then finally, the fourth mark is just for then saying what are you going to do next in order to do a full investigation. So to do a full investigation, we need to repeat the steps with more weights. And that is your fourth mark, just for saying that you are going to do multiple tests for different weights. So all 4 points to get the 4 marks. Okay, we turn over to 1D. So 1D asks, what could be done to improve the accuracy in this investigation? So accuracy, very important word here. What it means is what's going to help us get closer to the true value. Alright, so what's going to help us get measurements that are closer to the true value? So let's look at each of our options. And it says tick 2 boxes, right, and there are 2 marks, so we need to pick two of these options. First option, use a pointer from the spring to measure the length. Now that sounds sensible because we're going to try and get a more accurate value of the length, the original length and the new length, by using a little pointer to point more accurately at the spring. Sounds good, but let's keep looking at the others. Use a stronger spring in the practical. That doesn't seem like it'll have an effect on our measurements, really. So I would count that one out. Let's put a cross next to it. Use a new spring between each reading. That also doesn't sound too sensible to me because we want to look at a specific spring and how the force on it affects its extension. So we don't want to change the spring. Make sure the spring is stationary before measuring the length. That also sounds like a good idea because we don't want to try and make a measurement when the spring is bouncing up and down. We won't get a very accurate value. And then finally, use a longer rule when measuring length. So that one, using a longer ruler, I'm not sure how that's going to help us. So let's put a cross next to that one. And that leaves us with these 2. Use the pointer and make sure the spring is stationary. And those are 2 correct ones. 1 mark for each. Okay, 1E, the student added weights to a spring and measured the extension of the spring. Figure 2 shows his results. So we can see the results. And notice straight away, starts at the origin, straight line. That's going to be important for the next question. Let's turn over and see what the questions are. So what is the relationship between force applied and extension? Tick 1 box. So I'm going to turn back to the graph and just make a little note. So the fact we can see a straight line that goes through the origin, that means one thing, one very important thing. Straight line through origin. That implies a directly proportional relationship, right? So in this case it means that the force and the extension are directly proportional to each other. So with that fact, we should then be able to answer this question: what's the relationship between force applied and extension? It says tick 1 box, and the obvious box is extension is directly proportional to force because the graph is a straight line through the origin. Okay, the next question asks us to again use the figure to determine the additional force needed to increase the extension in the spring from 5 centimeters to 7 centimeters. So what we need to do is again look at the graph, and we want to know what's the force that we need to extend this spring from 5 centimeters to 7 centimeters. So first thing we're going to do is see how much force is required to actually extend it by 5 centimeters in the first place. And we do that by drawing up to the line and then looking across, and that's going to be 1.25 because it's halfway between 1 and 1.5. And then to extend it up to 7, let's see how much force is needed to get it up to 7 centimeters. So same method, drawing up to the line and then going across to give our force value, and that is halfway between 1.5 and 2, so it's 1.75. Now we need to be really careful because the question asks us what's the extra force needed to go from 5 to 7. So at 5 the force is 1.25, at 7 the force is 1.75, so the extra force needed is going to be the difference between them. It's going to be 1.75 minus 1.25, which is equal to 0.5 newtons. And that is the answer we are going to give for the force needed, is 0.5 newtons. Okay, then we're on to part G of this question. So table 1 shows some results with a different spring. So we see at 0, the extension is 0, which is what you'd expect. If there's no force, the spring can't be extended. Then 0.5, extension 0.025, force is 1, extension is 0.05, and force is 1.5, extension is 0.075. So if we look, we can see that as we go, I'm going to use the blue pen for this, as we go up by 0.5 each time, the extension is going up by 0.025 each time. 0 up to 0.025, and then 0.025 up to 0.050, so that is a change of 0.025, and then same thing going from 0.050 up to 0.075, again it's a change of 0.025, which should allow us to then make a prediction. So what would the extension be with a force of 2 newtons? So if we added on another 0.5, we would expect the extension to go up by 0.025 again, and 0.075 plus 0.025 is going to be equal to 0.100 meters, which is the last option, the last box here, and that's the one we should tick. Alright, then the last part of question 1. The spring constant for the spring in table 1 is 20 newtons per meter. Calculate the work done in stretching the spring until the extension of the spring is 0.050 meters. So the really important thing about this question is work done. Right? The work done in stretching the spring. What we need to realize is that, and remember, work done is equal to energy transferred. So the work done on this spring is going to be equal to the amount of energy that's added to the spring when we stretch it, and the kind of energy store that's filled when we stretch a spring is an elastic potential energy store. So to solve this problem, we're going to need to calculate the elastic potential energy increase for a spring with a spring constant of 20 newtons per meter when it's extended by 0.050 meters. So down the side of the page here, we're going to put EP for elastic potential energy. In fact, probably better if we use EE. Now we don't know that, we want to calculate it, so I'll put a question mark, and the units, as with the units for all energy, is joules. Then we need to know the spring constant. We use the symbol K, and that is 20 newtons per meter. And then we need to know the extension, which is equal to 0.050 meters. Now the equation to calculate elastic potential energy is EE equals to 1/2 times K times E squared. That's extension squared. So the elastic potential energy is equal to 1/2 multiplied by 20 multiplied by 0.050 squared. And when we calculate that and multiply all those together, we are going to end up with 0.025 joules. And that is our final answer, and that is the amount of work done, so 0.025. Okay, so that is question 1 finished. So let's move on to question number 2. So number 2, again, similar topic here. A student investigated how the extension of a spring depends on the force applied to the spring. So the diagram shows the spring before and after a force, it says had been applied, should be has been applied. Okay, so this is the before, and A to B, the spring hasn't been stretched yet, so A to B is going to be the original length of the spring. Then we look over here, and so A to B, still the same place, so that's the original length. And then with this force added on, the spring has been pulled down to point C. So A to B was the original length. A to C is the new length, which means the extension is the distance from B to C. And that is the first question on this part. So complete the following sentence using letters A, B, C, D from the diagram. The extension of the spring is the distance between the positions labeled B and C on the meter rule. So A to B was that original length, A to C is the new length, and extension is new length minus original length, and that should be just the distance from B to C. Next question, what form of energy is stored in the stretched spring? So this is the form of energy we just calculated before, and it is going to be elastic potential energy. And you must have the word potential in your answer. If you don't have the word potential, then it is not going to get you the mark. Okay, turning over the page to the next part. So 2b, the results from the investigation are plotted on the following graph. All right. The graph shows the student has made an error throughout the investigation. So what error has the student made? Give a reason for your answer. So let's look at this graph. Okay, so we see we've got on the y-axis extension in millimeters, and on the x-axis we've got force in newtons. So what the problem we can see with this graph is that when the force is 0 newtons, we seem to have an extension of 50 millimeters. Now that is not possible. If there's no force acting on a spring, then the spring cannot be stretched out. It cannot be extended. So that is exactly our problem. So what error has the student made? What they've done is they have measured the length of the spring instead of the extension. And the reason for our answer, the reason we know that this is true, is because when the force is 0, the extension cannot be 0. So that's the reason why we know they've made this mistake. So extension can't be 0 when force is 0. So the error, they measured the length instead of the extension, and we know that because the extension cannot be 50 when the force is 0. Ooh. Okay, then we're on to 2b part 2. So the student has loaded the spring beyond its limit of proportionality. So this is a very important term, limit of proportionality. And if a spring goes beyond its limit of proportionality, then force is no longer, and I'm going to put this for short, dP, no longer directly proportional to extension. So we have to mark on the graph line the limit of proportionality of the spring and label the point P. So if we go back up, we're looking for a point on the graph where the force and extension are no longer directly proportional. Now where we see a straight line, that does indicate they're directly proportional. And up here we start to see a curve. So you are allowed a range of answers here. If you made a mark here at 5, that would be acceptable. So we could put the letter P there. But you could make the mark afterwards, right? And the last place you could put it is around about here at 5.5 newtons. And put a P there. But anywhere between those 2 points, between 5 newtons and 5.5, you could put P anywhere along there, and that would be acceptable, because that's where our line starts to curve, stops being a straight line. So the reason for our answer is because we can express this in two ways. We could say it's because after that point the line starts to curve, right? Or the better answer is to say after that point force and extension are no longer directly proportional. So let's put it that way. So after point P, force and extension are no longer directly proportional. Okay, let's go over the page on to the next question. So, last part of this question, 2C, and let's read it. The student uses a different spring as a spring balance. When the student hangs a stone from this spring, its extension is 72 millimeters. Now we need to be careful with that. If we're going to have to use that in an equation, we don't want it in millimeters. That's not the standard unit of extension. So we need to change it into meters, and changing it into meters would give you 0.072 meters. So I found that by dividing by 1,000. Then the spring does not go past the limit of proportionality. Calculate the force exerted by the stone on the spring. And we're told the spring constant is 25 newtons per meter. So we have to show clearly how we work out the answer. So we've got the extension and we've got the spring constant. So to work out the force exerted, right, we would use the equation F is equal to K times E. Before we do, let's see what we have and what we need to find. So F is the force, we don't know it, the units are in newtons. K is the spring constant, and it is 25 newtons per meter. And extension, I've already changed it, is 0.072 meters. Okay, so let's put those values into the equation. So F is equal to 25 multiplied by 0.072, and that will give us a final answer of 1.8 newtons, and that's what I'm going to put in here, 1.8. Okay, we're on to our last question, question number 3. So this one is about the human catapult. So the diagram shows the stages of an extreme sport called human catapult. Then 4 bullet points. A person lies in a cradle which is held to the ground. The cradle is released. The person is launched vertically into the air by an elastic rope. The person then parachutes back to the ground. Now, this is really important. Elastic rope, right? If the rope is elastic and it's stretched, that means there's going to be some elastic potential energy. And then if the person starts to move, if they start to move, they started at rest because they were held to the ground, but then they start to move. So if they start to move, then we're going to get some definite kinetic energy. But they are also moving upwards. So that kinetic energy is going to transfer into gravitational potential energy. So we've got three kinds of energy. We start with elastic potential energy when the elastic rope is stretched. Then when it's released, that's going to transfer into the kinetic energy store. And then as the person moves upwards, that's going to transfer into a gravitational potential energy store. So let's see what the questions ask us about this. So 3A, in position A, there is a store of elastic energy. Position C is the person's maximum height. So describe the energy transfers from position A through position B to position C. So let's take this a little bit at a time. So 3 marks. The first one is we need to say at particular points, so between A and B. Now we know between A and B, that is where the person goes from being right on the ground to being a little bit up. We know that between those 2 points, the elastic rope is starting to move back to its normal size, which means between A and B, the elastic potential energy store decreases. So that's our first mark. Between those 2 points, the elastic potential energy store decreases. And then our second mark is to say that between A and B, the kinetic energy store increases and the gravitational potential energy store increases. So we need to say that both of them are increasing between positions B and C. And that's our second mark. And then the third mark is to talk about just B and C. So this is a little bit tricky, but between B and C, the person is no longer being pushed by the elastic, which means the kinetic energy store is actually going to start decreasing because it's being transferred into gravitational potential energy, because between position B and C, the person is going up, 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 higher and higher, so they're getting more gravitational potential energy in that store, but that is coming from the kinetic energy that they had. So the third and final mark is to say between B and C, the kinetic energy store decreases and for short I'm going to write the GPE, gravitational potential energy store, increases. Okay. 3B. In the last few meters of his descent during the parachute stage, the person travels at a terminal velocity. Explain why. So this is a concept that we looked at in year 9, terminal velocity, and it's when a person falls at the maximum possible velocity. And 2 important things about that. Terminal velocity is reached when the resultant force is equal to 0. Right? That's absolutely crucial. And also that's going to happen when weight, so the weight pulling the person down, is equal to the air resistance pushing against them. So we're going to use that to help us get these 2 marks. So it says, explain why this person reaches a terminal velocity, and the first mark for this is to say that the weight and air resistance are equal, but they're also in opposite directions. So they're equal and acting in opposite directions. So that gets us the first mark. If you just said the weight and air resistance are equal, that would be fine and you would still get that first mark. And then the second mark is for then pointing out that that means the resultant force is 0. And that is the second mark, and that explains why the person travels at terminal velocity. Okay, we're on to our final question. So when stretched in position A, the elastic rope stores 25,000 joules. The elastic rope behaves like a spring with a spring constant of 125 newtons per meter. So here, 25,000 joules, that is an amount of energy, and it's energy from stretching, so it's actually elastic potential energy. And then we're given a spring constant, so that's K, and we want to calculate the extension. So there is one equation that links these 3 things, which is that the elastic potential energy is equal to 1/2 times the spring constant times extension squared. So let's write down what we have. So we are given the elastic potential energy, 25,000 joules, and we are given the spring constant, which is 125 newtons per meter, and we do not know extension, so let's put a question mark, and the unit for extension, the standard one, is meters. So let's put what we have into the equation. So 25,000 is equal to 1/2 times 125 multiplied by extension squared. So to get extension by itself, we're going to divide both sides by 1/2, and we're going to divide both sides by 125. So what that's going to give us is E squared is equal to 25,000 divided by 1/2 times 125. And that's not, though, going to give us extension if we do that, because that's extension squared. So the extension is going to be equal to the square root of 25,000 divided by 1/2 times 125. And when you work that out, you end up with an answer of 20 meters. So our extension over elastic rope is 20 meters. So in terms of the 4 marks, you would get 1 mark for correctly writing down the equation, 1 mark for substituting in the values, the 3rd mark would be for doing the correct rearrangement in terms of division, and then your final mark is for doing the square root and getting the correct answer. So that is the end of this week's Year 10 homework. Thank you very much.